Hello students, Mr. Allen here. Today we are going to look at two more sections in chapter 6. Section 6.3, which is on proving quadrilaterals are parallelograms, and section 6.4, which is properties of rhombuses, rectangles, and squares, which are also parallelograms. Our objective today is to determine whether a quadrilateral is a parallelogram, to define and classify special parallelograms, and to use properties of diagonals of rhombi or rhombuses and rectangles. So let's go and look at example 1. So I'm going to do things a little bit different today. Instead of giving you a theorem first and then proving something, I want to prove something. So what I want to do is I want to prove that this quadrilateral ABCD is a parallelogram. We're given that AB is congruent to CD. We're also given that AD is congruent to BC. So that's our given information here, step 1. So again, remember what I'm trying to do is prove that this is a parallelogram. And remember, we found out last time that a parallelogram is a quadrilateral with its opposite sides parallel. So step 2, why is BD congruent to BD? Well, that's our reflexive property. We've used that quite extensively in this class. So that means that this segment is congruent to itself. And now in step 3, it says triangle DAB. So DAB. So D, that's corresponding to B. So that's going to be BCD. Triangle DAB is congruent to triangle BCD, and that's going to be, of course, by SSS, because I have 3 corresponding sides congruent. Now it says, step 4, angle 1 is congruent to what? Well, it's going to have to be, if this angle 1 here is corresponding to angle 3, so that's going to have to be 3. And we could use that by comparing the corresponding parts of those 2 congruent triangles. Angle 4 is going to be congruent to angle 2. Again, those are corresponding parts. And that's by CPCTC. So now, step 5, segment AB is parallel to CD and segment BC is parallel to DA. Why would that be? Well, that would be because of the alternate interior angles converse. So if we know that the alternate interior angles between 2 lines in a transversal are congruent, then those lines are parallel. And then finally, we can conclude that this is a a parallelogram by the definition of a parallelogram. And again, you might be thinking, okay, Mr. Allen, great. You just made a proof to prove that this is a parallelogram. Well, I want to show you why this section is so important, this section 6.3. So this took me 6 steps to prove that quadrilateral is a parallelogram when I knew that this side was congruent to this side and that side's congruent to that side. So what I'm going to do now is in section 6.3 is we're going to see all the theorems that we could have used instead of this, for example, that would make this a lot shorter and easier to show. And that's actually the title of this section, proving a quadrilateral is a parallelogram. So here's the first one. It says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if this side's congruent to this side and this side's congruent to that side, then we can conclude it's a parallelogram. By the way, this is the symbol again for a parallelogram. That theorem would have been very handy on our first little proof. In fact, let's go back to this proof again, except now we're going to forget all of that. If we know that this side is congruent to this side and this side is congruent to that side, step 1 is just going to be the given again. And then step 2 is going to be that A, B, C, D is a parallelogram. And then the reason is going to be, and I guess this should be over here as well. The reason is going to be theorem, and we'll go back and look at that theorem one more time. Theorem 6.8. Theorem 6.8. In other words, instead of doing 6 steps, since we have theorem 6.8, we could do that in 1 step. So all you need to know is that opposite sides are congruent, and you can conclude it's a parallelogram. So that's one way we can prove a quadrilateral is a parallelogram. Here's another one. It turns out that if angle A, that's this angle here, if it is supplementary to angle B and it's supplementary to angle D, then this is a parallelogram. Now, I'm going to tell you right now, I think this one is the most difficult to remember. So if I were you, I would mark this guy down as a star, and I would make sure I add that to my notes to remember to do that. Supplementary, by the way, remember, means they add up to 180 degrees. Theorem 6.10. This is another way to prove that a quadrilateral is a parallelogram. So this one says if both pairs of opposite sides of a quadrilateral, both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. In other words, if this angle is equal to this angle and this angle is equal to that angle, it has to be a parallelogram. And theorem 6.11, this one talks about the diagonals, like these here. If the diagonals of a quadrilateral bisect each other, in other words, if this diagonal bisects this diagonal into two congruent pieces, and similar, this one's divided into two congruent pieces, then it has to be a parallelogram. So those are the ways to prove, oops, I got one more here. This was the final way here. So this one, we have one pair of opposite sides of a quadrilateral, both parallel and congruent, then it has to be a parallelogram. So if this side's congruent to this side and this side is parallel to this side, then we can conclude it's a parallelogram. So over here, we already know that this side's congruent to this side. Well, these two angles are supplementary, so this side has to be parallel to this side. So therefore, this is a parallelogram. All right, so let's look at an example here. So this example, we're supposed to find x and y, and we want to do this in such a way that guarantees us that this is a parallelogram. If we want this to be a parallelogram, then this side has to be congruent to this side. In other words, x plus 2 has to equal y. And this side have to be congruent as well. In other words, 3x minus 5 has to equal 2x plus 1. So now we've got a system of equations, and we need to solve that. So I'm going to actually work with this equation here. Let me show a little bit of work here. Here are our original equations. I'll call this equation 1 and equation 2. Now I'm going to work specifically with equation number 2 here. So I could minus 2x, and then I could plus 5, and then I could plus 5. So that's going to give us x is equal to 6. So x has to be equal to 6. And if x is equal to 6, let's just double check that that makes sense. That's going to be 18 minus 5, which is 13. And then that'd be 12 plus 1, which is 13. So that's good. So now we've got x is equal to 6. Now we can substitute that back up into here. And we'll do that in, let's say, I don't know, let's do it in blue. So 6 plus 2 equals y. So y is equal to 8. So the answers for this particular question are x is equal to 6 and y is equal to 8. And I think we saw here, if x is 6, then this side's length was 13 and this side length was 13. And if y is 8, then this side over here is 8, and then this side over here, x plus 2, which is 6 plus 2. Well, this side's also 8. So this is indeed a parallelogram. All right, example number 3. Can you prove that the quadrilateral is a parallelogram based on the given information? So we've got two parts here. So this first one says that this side is 5 and this side is 5, and it's also given that that's 50 and that's 130. Well, we've got one side congruent to one side. Oh, and we should note that 50 plus 130 is equal to 180. So these two guys are what we call supplementary. And if they're supplementary, then that means that this side's parallel to this side. Okay, and so then if we wanted to, we could go back and use this theorem right here, theorem 6.12. Theorem 6.12 says that if one pair of sides is both parallel and congruent, it has to be a parallelogram. So I would say yes. Now I'm not going to go ahead and write a detailed proof here, and this is by theorem 6.12, but I've given you the outline basically of the argument. So let's look at B. B says that HI is congruent to KH or HK, and JI is congruent to JK. So is that guy a parallelogram? Well, let's look at this. We actually don't have any opposite sides parallel or congruent. We have consecutive sides, adjacent sides congruent, but that's all that we have. So this is no. You cannot prove that this is a parallelogram based on the given information. So here this is a summary of the different ways to prove that two parallelograms, sorry, I get caught up in triangles. Two quadrilaterals are parallelograms. So there are, in this case, 6 ways. You could use the definition, which is what I did kind of in the first proof. Theorem 6.8, which says that opposite sides are congruent. Theorem 6.9, which says that if one angle is supplementary to consecutive angles. Theorem 6.10, which says that opposite angles are congruent. Theorem 6.11, which says that the diagonals bisect each other. And Theorem 6.12, which says that if one pair of sides is both parallel and congruent. So those are the different ways. There's 6 ways for you to be able to prove two quadrilaterals are parallelograms. So that's the end of section 6.3. So now we're going to look at section 6.4, which is based on 3 things: rhombus, rectangles, and squares. Let's just go ahead and start from the bottom to the top, work our way up to the top. Most students are pretty familiar with a square. Here is the definition, and I said these are key definitions. These are important. A square is a parallelogram with 4 congruent sides and 4 right angles. A rectangle is a parallelogram with 4 right angles. And a rhombus is a parallelogram with 4 congruent sides. Now notice that all 3 of these geometric things, these are all quadrilaterals, but more specifically, they are all parallelograms. All of these things are parallelograms too. So this is kind of a subset of parallelograms. They're referred to in the book as special. So theorem 6.13 says if a parallelogram is a rhombus, then it turns out that the diagonals are perpendicular. It's interesting. Theorem 6.14 says if a quadrilateral is a parallelogram, then the diagonals bisect their opposite angles. In other words, this diagonal, since this is a rhombus, makes angle 1 and angle 2 to be congruent. It also means that angle 7 and angle 8 are congruent. 5 and 6 are congruent. In fact, I should be using different markings here. Sorry about that. Turns out all those angles are going to end up being congruent. Let me say that more correctly. Angle 1 and angle 2 are going to be congruent. Angle 5 and angle 6 are going to be congruent. And similar, actually 1, 2, 5, and 6 are all congruent. And then 7, 8, 3, and 4 are all congruent. So they're not all congruent. Angle 7 does not necessarily have to equal angle 1. So let's look at an example for 4. This one says, what are the measures of the numbered angles in this? And notice it says rhombus. Well, if it's a rhombus, I can already tell you with angle 1 has to be 90 degrees. And the reason that this has to be 90 degrees is because our first theorem, which says that if it's a rhombus, then the diagonals are perpendicular to one another. So that's our first answer. I'll get that one right out of the way. And by the way, if this angle is 58, guess what has to be true about angle number 2? Well, oops, I'm still on the eraser. The measure of angle 2 has to be 58. And the reason the measure of angle 2 has to be 58 is because this side has to be parallel to this side, This is what we call a transversal, and those are alternate interior angles. Oh, by the way, if angle 2 is 58, so does angle 3. Because if this is a rhombus, these diagonals bisect it. So this angle has to be congruent to this angle. So I know angle 1, I know angle 2, I know angle 3. The last thing I got to do is I got to figure out what the measure of angle 4 is. Anybody remember how to do that? Well, I'm going to draw this triangle down here again, kind of. We said that angle 1 is 90, so that's 90. We said that angle 3 is 58. So now the question is what's this angle over here? Well, we're just going to use our triangle sum theorem. So we just need to subtract, and that's going to give us 32. It's 32 degrees because all three of those angles have to add up to 180 degrees. So when you add 32 to 58, you get 90, and 90 plus 90 is 180. Theorem 6.5 says if a parallelogram is a rectangle, then the diagonals are congruent. In other words, this length here, that's segment AC, has to be congruent to segment BD. So if it's a rectangle, and if you can pretty much almost just look at that and tell that those are the same. So let's look at example 5. It says in rectangle RSBF, SF is equal to 2x plus 15. That's this right here. This length right here is 2x plus 15. And then it says that RB is 5x plus 12. So this right here is 5x plus 12. Well, since this is a rectangle, and the reason we know it's a rectangle is because they tell us it's a rectangle, we know the diagonals are equal. So we know, I'll put it this way, that the diagonals are equal, or we'll put it congruent, it's probably a better way of saying that. So SF is congruent to RB because they are diagonals. So SF is equal to RB. In other words, 2x plus 15 is equal to 5x minus 12. And now I'm going to go ahead and solve this equation. Minus 2x, minus 2x. So I'm going to get that over here. So I'm going to plus 12 here, and I'm going to plus 12 there. That's going to give me 27 equals 3x. X is equal to 9. But that's not what the question is asking us for. The question isn't what is the value of x. The question is what is the length of the diagonal. So now what I'm going to do is now I'm just going to substitute this back in here. And I'm going to say that SF is equal to RB is equal to 5 minus 12. And then I'm going to put this times 9 in here because that came from this. And so we're going to get, what will we get there? We're going to get 45 minus 12 would be 33. So it's 33. The length of that segment or that diagonal is 33. All right, we're getting pretty close to time here. Let's go ahead and wrap. Oh, that's it. Woohoo! We are close to time and we are done. Thank you guys for your attention. And that is section 6.3 and 6.2 or 6.4.